Hello and welcome. In this video, I'm going to take you on a very exciting journey into a fractal world. So at the beginning now, I'm just going to show you, because I didn't do it in the last video of the series, which is called Fractal Raymarching, I'm going to show you how to play around with these fractals yourself, because the question popped up quite a number of times now. So you are on my channel here, and this is the first video of the series. So let's go there. In this video, I presented you the Menger sponge, and I showed you quite an interesting journey through this very simple geometric fractal. If you go into the video description, you find a link to my GitHub, or at least one of my GitHubs. And the only thing you have to do here is click on code and then download the zip. Additionally, you need to click this link and download Glue 2.1 DLL, which is necessary, the Glue 32 DLL, to run the program. So if you go into here, the basic thing you need for just playing around is release. You also have the other project files in case you want to take a look at some of the source code of the framework, but for playing around with the fractals you do not need to build it or to do anything with the source code, but you just have it there in case you want to build it yourself, especially if you have 4K screens. Then you need to build it yourself because the release build is made for HD. So inside the release folder, there is everything you need. The texture folder is quite irrelevant, you do not need it, but it's still in there and I don't know if you can remove it. That is the executable. This is needed to actually start the program and walk around the fractals. And inside the GLSL fragment shader is the whole code for the fragments, for the fractals, and the fragments of course. It's basically a pixel shader. And last video I gave you some nice introduction into how diffuse shading and specular lighting, ambient occlusion and so on works using a ray tracer. And it also contains the code for the Menger sponge fractal. In this video, in the description as usual, I'm going to make a new project in the GitHub and just upload this file, because that's the only thing you have to replace to take the already existing framework and just replace that file in the release folder. So on my local file system, you can see it here, that's the file, that's the Glue 32 DLL, and in this configuration everything works fine. So below this video you are going to find a link for just this file and nothing else. And everything else you have to take from the old video. So now, without further ado, let's take a look at the fractal. So welcome back. I hope you liked the little tour through the fractal you just saw. And for those of you who are still around and are interested a bit more into the technical and mathematical details, I'm going to give you a short overview. So if you remember the source code, I start with the void main and nothing changed here. This is, as you might remember, just setting the ray position and the ray directions and passes everything to the void render, the vector-free render. So the render function takes in the ray origin and the ray direction, and it's going to do all the lighting. And the drawing of the fractal or the geometry itself happens in the function intersect. So everything else here is ambient occlusion, specular lighting, diffuse lighting, fog. So all the things I basically covered in the last video. And if you're interested in the basics of that, go check it out. The manga sponge is maybe not as an interesting fractal as this one, but it's nevertheless worth a look. It's actually the starting point, so one of the most simplest fractals you will find. Nothing changed in the little helper function to calculate the normal of the surface. I use this for shading and coloring and all sorts of things. And nothing changes in the function intersect. So I told you the geometry is generated in the function intersect, and this is basically just propagating a ray through the geometry and detecting if there is a hit. And the geometry itself, so the ray gets propagated in this loop here, and the geometry itself comes from the function map. So you see, it really didn't change much compared to the last shader. The function map only has some slight adjustments. I set the world position a little bit shifting in the Z direction, which is up and down, and the Y direction which is front and back. Or yes, front and back. So I just added some little shifting here so that I don't start underneath the surface, which is quite annoying because then you don't know where to go and you have to find a way out. I also apply some scale to scale the whole world to a factor that is convenient. But the geometry itself comes out of the function mb. Also, the old function de is still in here, but let's take a look at the function mb. So this is the function where the entire geometry is generated from. The entire fractal just sits in here. Everything else is a bit of shifting, scaling, ray propagation, lighting, coloring, and ray directions and camera settings and all of this. So really this is the only interesting function you're looking at basically. Quite nice, right? So what are we dealing with? In this case, we are dealing with a variant of the Mandelbrot set. So I guess most of you know what the Mandelbrot set is. You see a picture right here, and many of you have probably seen one of these Mandelbrot zooms, so if you're interested in fractals, there's basically no way to get around seeing one of these. I mean, they are quite amazing. And the Mandelbrot set is located in the complex plane. So if we go to its formal definition, we will see that this is defined by a recursive equation, and C is a point in the complex plane. So to take this fractal and move it up into the third dimension, what is basically done is, instead of a two-dimensional point in the complex plane, one is going to take a three-dimensional point. So there is not really a three-dimensional equivalent to the complex plane, at least I do not know of one, but you can adapt the mechanics. So if you take a look at this equation, there are basically two things that are important mechanics to calculate this recursion formula. The first thing is addition, and complex numbers can be represented in a rectal-like shape. And if you add them component-wise. You add the real part and the imaginary part, or if you look at them as vectors, you add the x and the y coordinate independent of each other. This addition here is very easy to scale up to higher dimensions. You just add component-wise for every dimension. So if c gets 3-dimensional and zn squared also, it's no problem. You just add x, y, and z coordinates instead of just x and y. So that's the first problem already solved. Then there is a second problem, how to square. And there is actually quite a nice way on how squaring on complex numbers is done. So let's navigate to the complex numbers and take a look at multiplication. So there are multiple ways on how to multiplicate two complex numbers. You have one form that takes the vector form and somehow mixes and merges their individual components, or you can represent them in polar form. Polar form is nothing else that instead of two coordinates, you have an angle around the origin and you have a distance to the origin called r, or the magnitude of the respective complex number. So if you have two complex numbers, the first one is given as r1 times the cosine formula and the respective angle. So this is the angle around the origin of the first one, and that's the distance from the origin of the first one, and you have the same for the second one. Then you can multiplicate them by multiplicating their distances from the origin and adding up their angles. And something very similar can be extended to multiple dimensions. So let's take a look at the implementation in the function mb. So the interesting part, basically, it takes place here. Iterate. So that is nothing else than applying one iteration to the equation. So we have r, which is for our 3-dimensional point, the distance to the origin, and we take this to the power because let's say we want to square it, then we would square it, and in this case I have a power of 8. So that's another difference to the Mandelbrot set. I'm going to use a power of 8 instead of 2, but it's not really a problem. So we take the distance to the origin and power it by 2 for the Mandelbrot set, like you see here, or by 8 for the fractal I draw here. So it's really a close relative of the Mandelbrot set. And then we have two angles. In fact, we have now spherical coordinates. So if we take a look at spherical coordinates, you see, just zoom into that image if I can find it here. You see we have basically the same as with polar coordinates. We have the distance r from our point to the origin, and we have two angles. This one is, I guess, theta, and it's the angle, the elevation angle basically, and then we have phi, which is the rotation around the z-axis. So we have two angles and one distance instead of one angle and one distance. And we basically do the same as we did in the ball coordinates by complex multiplication. we are taking the distance to the power, we square it or take it to the power of 8, and we add up the angles. In this case we add 8 times the same angle. For power equals 2, or for squaring, like we would do in the Mandelbrot set, we would just add the angle to itself for both angles. And then we are going to convert it back from its spherical coordinates to its usual Euclidean vector coordinates with x, y and z coordinates. So it's basically always the same step. We come in here into the iteration and we are going to update the individual modules by converting them here to spherical coordinates. Then we apply the iteration step and we convert them back to Euclidean coordinates. So we found a very nice way on how to extend this formula, which works for complex numbers, for a three-dimensional kind of equivalent of complex numbers. We really just copied the multiplication and addition mechanics, but there is not really something like three-dimensional complex numbers. It's just that we took some of their mechanics and some of their behaviors and scaled it up. And that's exactly what this function is doing. I mean, the detailed things like why here is an A10 and what the sine and cosine functions are doing, it's a little bit too much for this video. But the only thing I want you to take away from this video, at least I'm doing my best, is that we are very close to the Mandelbrot set. And there is really not much that I did. I mean, I changed the power here, I added one dimension and somehow tried to preserve the dynamics of the original Mandelbrot set. I added some little twists that we get a nice terrain. But in the most part, it's really basically the Mandelbrot set in a three-dimensional version. So you can explore the interesting parts of the Mandelbrot set now in full 3D and enjoy its entire beauty. I mean, it's already beautiful in 2 dimensions, but I think it's still another experience if you can really walk through this totally surreal world. So finally, I hope that you liked this video. There will be definitely more in the next time. I try to upload 1 video every week. There will be chemistry next probably, because the weather is finally getting better. And I have a lot of my experiment setups ready, and I'm just waiting for a good weather period to start off with chemistry. But of course you will be seeing math videos and fractal videos and coding videos and all sorts of things that I'm doing in my free time. So that said, thank you for watching and have fun playing with the fractals.